So I know some of you guys haven't studied game development, okay, game design development before. So before we start to learn all the things about Unity, so I would like you to learn something about the game architecture first. So what is the basic structure of a game, and then how it can display the 3D graphics, and then what is the model, animations, and also physics inside. So here we will give you some overview of the game structure. Yeah, games and other VR or AR application, they are computer applications. Okay, so for all the computer application, they belongs to the same workflow. Okay, same flow. So you have the input, process, and output. Okay, okay. So they gather the inputs from your hand, or in our case, you will get somehow about the natural language processing, or even using the webcam. So they are input. And then here we have different algorithms, we have different game engines, we have different API to do the process. Okay, and then output the screen. Okay, output the screen to your eyes, output the voice to your ears. And somehow if you have enough time, so you can also output the things into VR, so you can have vibrations and then let their hands to feel your gameplay. So what is the things inside input, process, and output? So here we were talking about the technologies behind one by one. So the first thing is the input, and then the well-known thing is the keyboard and mouse. Okay. So yeah, it's the core of all the computer application, including the games and also other kinds of VR applications. Sometimes they also use the keyboard and mouse, and then they only use the head-mount display for the graphic display. And if you are working with the game console, so you have gamepad, okay, gamepad and joystick. Okay, so a special device for you to input the game the control to your games. Okay, so they limit the input into 6 or sometimes 8 buttons. Okay, together with the analog. Okay, to move and also change the position of your viewpoint. Okay. And then if you are VR device, so somehow we use the VR head-mount display. Okay, VR head-mount display. So for the VR head-mount displays, most likely they will capture the input of your head. Okay, and then your head positions and also your head orientations. Sometimes it also capture your hands position and orientation, so you can get more about your body movement. So if you you can pay more and more about your hardware device, then you can also capture the full body movement. Another common input is microphone. Okay, so today natural language processing (NLP) is pretty good. So most likely we can use the microphones to capture the voice input and then recognize the keywords, and then because we have the keywords, and then we can process the computer to continue the gameplay. So after the input, we have process. So the process can be easily divided into 3 parts. Okay, so well-known CPU, GPU, and CPU. Okay, CPU means that central processing unit. I guess all of you guys are well known about this one. So the CPU most likely is about the thinking process. That means the gameplay. Okay, all the logics behind, all the if-then rules, or whether um, your HP is going to increase or going to decrease, or whether you go to next level or not, or whether you can unlock the next level or not. Okay, so those are the gameplay, those are the logic, so it belongs to the CPU. Another part is the GPU. Okay, so GPU, graphical processing unit, so they have special command inside the processing unit. So CPU, so most likely is basic ALU, they do the basic calculation, but GPU, they focus on the graphical part. So they focus on the vector, they focus on the matrix. So they focus on the floating point calculation. So some of you guys, if you are going to go to the fintech or going to study about the AI, we always need to go. We always need to study about the floating point. Okay, floating point. So that's why the GPU is also famous for the blockchain calculation. Is also famous for the security calculation because they can handle the floating point very well. They are designed to handle the vector. They're designed to handle the matrix, etc. Okay, so they are responsible for the rendering and display. Okay, all the calculations about the graphics they goes to the GPU. PPU, so it's a new term. Okay, so full name is physical processing unit. So today, when you are going to do some physical or physics simulations, for example, so calculate about the flow of the water, calculate the flow of the air, the smoke, etc. So you calculate lots of the physics. That means the Newton's law, okay, or other particle effects, etc. So you need a special processing unit. So there are lots of physical command inside. Okay, F equals to ma, and also all the Newton's law, and also all the physical equations. Okay, so the GPU is most likely is used to move or interact. Okay, interact with all the physical body inside. That is the process part. So the output after the CPU and the GPU will process the informations, and then they will refresh the screen. Okay, so they will compile all the things into one 2D. Okay, whatever they are using the flat display or they are using the VR display is only 2D display. So they compile all the things, all the information into a 2D screen. Okay, a 2D picture only, and then they refresh the picture one by one. So for the VR system, most likely we have a higher refresh rate. So minimum is 90. Okay, minimum is 90. Okay, for the flat screen display, so we can accept 50, or we mostly we accept 50. Okay, so the minimum is 50. We'll also output the sound system. Okay, so today you have 2.1, and then if you are looking for some better sound display, so you have 5.1, 7.1, etc., etc. You can also create the vibrations. Okay, force feedback to the gameplay so that the user can feel the physical. We can simulate the physical conditions to the user, to their hands or to their body. And of course, because yeah, here RAM. Okay. CPU cannot process all the processing unit. They cannot put all the data inside. So you need a RAM dedicated to store the data into it, and then get out for the processing. So you have different processing units. So you have different RAM. You have RAM, you have VRAM, and then you have the RAM for the physical processing unit. So there are some dedicated RAM or cache for you to do the data storage. 3 or 4 years ago, so we update all the machine in our lab. So now today, not really good. 3 or 4 years ago, they are the top, but now it's not the top. Our lab, they are using 1080, okay, or 1080 Ti. So we have this kind of GPU inside our lab. All the machines, they have this kind of settings. So after the hardware, of course, you have the software, okay, software standard, okay. So you have the OS level, okay. So whatever you are running in Linux, Windows, or Mac OS, you have the OS level. And then you have the middleware, okay. Middleware consists of two kinds of things. So one is the HAL, hardware abstraction layer, okay? So mostly you have heard about the DirectX for the Windows system, and also you have heard about the OpenGL for the others, okay? Mac OS and the others OS system. So they try to handle the communication with the hardware. So we'll discuss later. And then on the top of the HAL, hardware abstraction layer, and then you have the game engine. Okay, so the game engine helps you to handle all the things about the, yeah, because today nearly all the games they have similar calculations. So you need to handle the graphics, you need to handle the physics, you need to handle lots of things about the asset control, asset management. That means the model, that means the animation, etc. So you have another thing called game engine. Game engine, they provide all the fundamental background so that you need not to write the code directly using the directs. Okay, so yeah, this is the middleware, and then finally is your games, okay, or your 3D application. So you build in your logic, you use the algorithm of the middleware, you use the API of the middleware, and then compile all the things into your games or 3D applications. Okay, that means you write the logic to do all the things. So here is the structure of the game. So most likely you have the hardware first, and then you have the driver. Okay, so wherever you are running the display card, or wherever you are running the sound card, yeah, or the motherboard or other things, right? You need a driver. Okay, so there is a DDI, device driver interface. Okay. Many years ago, around 30 years ago, 30, yeah, almost 30 years ago. So there are lots of display card, and then they do not have a standardized interface. So based on different display cards, based on different drivers, so we need to use different programming to implement different driver. So at that time, 30 years ago, when you playing a game, so there are different versions of the game, and they deploy into different display card. So at that time, it is our nightmare. So it's a program for one games, and then you need to have different kinds of versions, and then the code cannot be reused. Most likely it's only the logic you can reuse, for the other you cannot. So to speed up the development of all the 3D, okay, of all the you have the display card, so you have the 3D applications, right? To speed up the development of the 3D applications. So Microsoft, they design a HAL, okay, hardware abstraction layer, okay. So they standardize all the display card driver, and then on the top of the display card driver, we use a common SDK to develop the games on it. So the HAL, hardware abstraction layer, now we are still using, and there are two well-known HAL. One is Windows platform, so it's DirectX, okay, DirectX. So you have Direct 11, Direct 12, etc. Okay, so depends on the version. So they support different kinds of the shader. They support different kinds of visual effect. Another things beside the Windows platform, behind the export platforms, right? So you have another called OpenGL, okay? So these two, OpenGL and Direct HAL level, so they provide standardized codes for you to develop the application, and it really speed up the development of all the 3D applications. Okay, so you only you only have two versions, and then you only compile your code into two different kinds of HAL, and then you can deploy to all machine. Okay. So on the top of the HAL, and then you have the direct 3D, direct sound, direct input, etc. API for you to call. And then finally, all your 3D application will be put into Win32. Okay, Win32. So it's similar to all the 2D application. 2D application is here, so you have the graphical device interface, and then finally they go to Win32 or Win62 application. That means all the things inside the Windows, they are running the 3D, but outside you also have the Windows status bar. You can minimize, maximize, or close the applications. So what's inside a 3D animations or a games? Pawns, okay, lots of the pawns here. So all the pawns are located in a 3D space. Okay, so all the pawns they have their X, Y, Z positions, and with three pawns joined together, it becomes a face. When lots of the face together, it becomes a polygon. Okay, so here is a polygon. Okay, and a polygon is a model. And then to control the model polygons, so we need a skeleton. Okay, so here
is a skeleton. Okay, skeleton can be a biped. So this one is a biped, is a human structure. We call it humanoid. Okay, humanoid skeleton. You can also change it into different style of skeleton. For example, you can add a tails. For example, you can add another hands to change it become a monster, etc., etc., etc. So the skeleton here is a humanoid skeleton. It's a human style, and then each of the skeleton they will control a set, okay, a set of pawn, okay, okay. So when you move the skeleton, they will control the corresponding pawns to move, okay, okay. And then besides skeleton, you also have the animations, okay. So the location of each skeleton, okay, each part of the skeletons will be recorded in every time frame, okay. So it depends on the details of your games or video animation. Perhaps it will be 25 FPS frame per second. Perhaps it will be 50. Perhaps it will be 100 frame per second. So in every frame, they will record down all the positions of the X, Y, Z, okay, of each part of the skeleton. So by control the skeleton, you can give the animations to the 3D model, okay? So most likely, all the games or video animation beside the VRs or beside the motion capture, okay? So nearly all the animation, they are pre-recorded. They are pre-recorded X, Y, Z information regarding to the time frame. So here is some more information about the skeleton. So skeleton is a hierarchical set of the interconnected bonds. Okay, and then this one, the envelope here, the envelope, we call it visit modifier in Video Studio Max. So most likely in the game engine, we will not process this kind of animation. So we will record it in 3D Studio Max, Maya, or Blender, and then we will import it in Unity, in 3D games, or other applications. So here we'll talk about the vector and then the display pipeline. Okay. So in a 3D world, so somehow we are using vector to control all the coordinate. Okay. So it's a 3D coordinate system. So here is X, here is Y, okay, and here is Z, okay. So for a character here, it's moving on a X, Z plane, okay. So if the character jump, then we are going to move his Y coordinate, okay. So X, Y, Z is the coordinate system inside the 3D world. And then inside the 3D world, we also have a camera. So a camera also have a position. So the position also contain X, Y, Z information. And it also contain a vector called look at. So what is the point that you are going to look at? So here, another X, Y, Z informations. Okay, so we are using three vector to control this camera. Okay, so similar to our eyes information, we can only process the things in 2D. Mostly we can only process the thing in 2D if the distance is far than 6 meters. So we will compress all the things inside the 3D world into 2D. Okay, into 2D, and then change the world coordinate into wheel coordinate. Okay, so the wheel coordinate we only have two, X and Y. Okay, okay. Paper Mario is a little bit special. So this game is Paper Mario. So Paper Mario is a 2.5D. So the camera setting is, we call it parallel projection. It is a little bit different from our ice ball. For our ice ball, I will explain another one perspective projections later. So XY here, we will compress all the things together, and then according to your screen, so we will chop the coordinate into another xy. So the coordinate origin starting from here, x, y, okay, and then turn it into your screen. So depends on whether it's a mobile display or whether it's a PC game monitor display or a TV display. So you change the screen coordinate. So as I have mentioned before, Paper Mario is a pair projections, but for our ice ball a little bit different. So we are quite perspective. Okay. So for the near objects, so here near object is bigger, See, the near object is bigger, and then for the far object, it's smaller. Okay. So it's not a cube or it's not a rectangle. So the projections of our perspective is this kind of models. Okay. So we have the near plane, and then we have the far plane. For all the things between the near plane and the far plane will be project. Okay, they will be compressed and then into a 2D screen. Okay, so we still have the world coordinate, we still have the view coordinate, and we still have the screen coordinate here. But the setting is a little bit different, and we still have the camera position and the camera look at positions. Okay. Game engine. Yeah, today, many years ago when we are talking about the game development, so 15 years ago when I teach the game development, so we teach you how to use the directs, we teach you how to use the coding and then type in the programming line by line. So for a simple video application, for example, if we want to put a clip inside video well, so it should be 4 to 6 A4 page that you need to code, okay, inside the directs. You do not have any graphical user interface. You do not have any fancy UI that you can do. The only things you can do is coding, typing the programming on your keyboard. Okay, so yeah, although the directs or the OpenGL they provide the quite user-friendly when you deal with the display card, but it's still a nightmare because you need to code a lot for the game development. Okay, so later someone start to design middleware. We call it game engine. Okay, so the game engine, they find that lots of the games. Okay, today lots of the games they share similar settings. They share similar library. That is, they have the gravity. If it's action game, they have the gravity. So you move on the floor and then you move to somewhere else and then you hit someone. Whatever is action game or shooting games, right? So you shoot a bullet or you use the weapons to hit the other. So somehow you have the similar physics. We call it game physics. That means the Newton law. And then you have the similar rendering system, and then you have the similar input to deal with it. So somehow lots of the gameplay, lots of the memory, or lots of the resources management, they can use the simple or they can use the standard working pipeline. So we have the game engine. Many years ago, we have lots of different kinds of game engine, but today we only have few, okay, 2 or 3 game engines left, okay. So yeah, perhaps you can name this kind of game engine. Okay, so 1 minute you can pause the video and spend 1 minute to guess this game engine. So this one, the best graphics that you can provide to you. We call it, they provide the next generation graphics. Okay, next generation graphics. Okay, so this game engine is Unreal. Okay, Unreal. So Unreal is used for the console game, or you are used for some big project. Okay, so mostly when you want to play the game inside the Xbox or inside the PS5, etc., they use Unreal. Okay, they use Unreal. It's pretty good. Okay, the rendering system and also the physics, they are perfect. They provide lots of the flexibility for us to do. And this game is overclocked, right? It's provided by the Unity 3D. So Unity 3D around 10 years ago, it tried to provide a simple solutions to all the individual game developer or small company. Today, nearly all the mobile game they are using the Unity 3D to do it. Okay. But the world is changing. So somehow, for the teaching, um, there are more and more game engines coming to become the competitor. So you call it core game engines, or if you go to mainland China, so there are lots of small game engine that is happening in Tencent or happening in the other game company. Okay, but by the way, Unity is still the common game engine that we are using in the whole world. And then, of course, you have some game engines for the beginners, or we call it for the 2D interface. So, for example, this one is RPG Maker. And then you can find lots of similar game engine, for example, Coco's 2D or some HTML5 game engine, for example, Phaser. So they are easy to use, but most likely they only focus on 2D. So let us have a look with the Unreal game engine.
Hello, I'm Siren, and I'm a digital human. I was created by an international team of artists and engineers who wanted to challenge our ideas of what a synthetic human could be. I've got state-of-the-art real-time graphics and an unprecedented level of detail in my eyes, skin, and hair. Cool, right? But I'm more than just a collection of fancy pixels. I'm actually being driven by a real human actress and her dynamic motion capture through Unreal Engine. So what are you waiting for? Come meet me at the Vicon booth and see for yourself.
So yeah, perhaps you will find this kind of animation easily in lots of Hollywood films, right? But try to remember, for all the film production, so somehow they take lots of the time to do the rendering. They are not real-time rendering. Okay, they are not real-time rendering. For game, we need real-time rendering. So as I have mentioned before, most of the game they only play the pre-record animations. Okay, pre-record animation inside the 3D model, so they can move and then they can run. But by the way, they are just changing your X, Y, Z positions. Okay, but the animation they almost the same. But Unreal is quite different, so they provide the real-time animation. They are real actors, they are real actors, and then they can do the real-time rendering. Okay, so this is quite impressive. If you want to know more, you can go to YouTube and then have a look with this kind of videos.
Hello, I'm Siren.
So as I have mentioned before, around 90, okay, so almost 30 years ago. So we have the first 3D games. We call it DOMs. Okay, DOMs. It's really popular at that time. It's a first-person FPS game. The architecture of DOM are quite well defined. So if you have time, you can just search game design document, okay, in the internet about DOM. So the full game design documents are here. And then they divide the system in a quite a manageable um, um, architecture. So they divide them into a three-dimensional graphical rendering system. They divide into a collision detecting system, audio system, art asset system. That means the resources management. And then they have the game world. Okay, so they try to separate. So they try to separate the world from different tasks. Okay, so become an individual one. So they can provide the professional graphic programmer to deal with the 3D graphics one, professional physics programmer to deal with the physics, audio program to deal with audio, etc. And then for the junior programmer, they can only deal with the game worlds. Okay, that means the interface or we call it logic part. Okay, so you create the levels one by one and then provide them to the user. This kind of settings are, yeah, they are reducing them, okay, reducing them, and then it become today's game engine, okay. because lots of the common library in different games they can share, and then we can reuse, and then we can use the same things to minimize the workload, and then we can speed up the 3D games productions. So here is game engine architecture. There are lots of different kinds of things. We will not discuss all the things. For example, later we can discuss about the collisions and physics. Okay, collision and physics. That means that for every 3D games, most likely you have the physics. You have, as I mentioned, you have the gravity, and then you have the collision detect. Okay, to detect where the 3D object touch another 3D object, and then you need to have some event to different. Okay, for example, decrease the HP, or for example, you want to change the visual effect. Okay, maybe it's a special visual effect, and then it represent someone is killed or someone is hurt inside our game. Okay, we will not change the 3D model, but most likely we will only use the particle effect, and then yeah, you add some texture inside it, and then perform into another status, and then we decrease the HP. That is how the game is running. Core of the game engine. Okay, so the most important thing is deal with the hardware. Okay, deal with the hardware. There is nothing important rather than deal with the hardware, because if you do not deal with the hardware, and then you have lots of the problems about you will throw exceptions because of the I/O, because of the graphic card, etc. Dealing with console, PS4, PS5, Switch is better because their hardware is standardized. Dealing with PC is really difficult because there are lots of different hardware combined together, and then for the I/O they always throw exceptions. So the best game engine is dealing with hardware without any throwing out exceptions. Okay, so they are going to deal with the driver, they are going to deal with the operation system, etc., etc. Okay, and most likely they are going to deal with the DirectX and OpenGL, this hardware abstraction layer. Okay, so one is for Microsoft, and other is for the other Mac, and also the open environment, for example Android, etc. So if you deal with the PlayStation that I have mentioned before, is console hardware. So you have another library called library GCM. Okay. And then for PlayStation, you also have another powerful tools called Edge to deal with their hardware, which can speed up their processing time. Unlike the general PC, the general PC is designed for lots of different applications. But for the game console, the command, the chips inside is only designed for game. So if they use the library GCM or you use the Edge, you can speed up the whole process. Core. Another core engine system. So you can think about the physics, you can think about the rendering, you can think about the sound, etc. But the core of the game engine is mathematics. Okay, that's why for the game developer or game program, you need to study the pure math, you need to study the physics, etc. So there are lots of error when you deal with the physics. Okay, when we deal with the physics. Yeah, our world is not only making of 3D, three-dimensional. Okay, three-dimensional is not enough for calculation. Even inside the 3D games, it's not enough. So most likely, besides the X, Y, Z, we have another three-dimensional. Okay, it's a complex number. So in your secondary school, if you have learned complex number in your mathematics, pure mathematics, like that. So you have the imaginary part I. Okay, so X, Y, C, and then plus I. But in our 3D world, we are not only using the one-dimensional complex number, we are using 3. So we have I, J, K to calculate the movement. So we have XYZ plus IJK 6-dimensional to calculate the whole 3D world, okay? And because the 3D world, they contain lots of the folding number, they contain lots of the one-off, so there are lots of the logical and mathematical mistake. And then the core engine is going to check, okay? Check and avoid the exception, 4 exceptions, okay? So it checked the mathematics with the line operations, with the ray tracing, okay, with all the 3D object, okay, geometric informations, matrix, vector, etc. So this is the core of the core inside the game engine to provide the fast calculations. Otherwise, if you have the GPU, you can do the floating point calculations. If you do not have the GPU, so most likely you have the CPU, right? Or in your mobile cam, you have the CPU. So you only have the matching table. For example, cosine 30 degree, it provides you a matching table. Cosine 30 degree to 40 degree, it provides you a value, which is a matching table. They are not going to calculate the cosine direct. They are only using the matching table. That's why the shader of the mobile phone or the games without GPU is limited. Okay, you cannot have a smooth shader. You cannot have a smooth shading inside your graphics because they do not have the math library on their GPU. Another core of the game engine is the resources management. Okay, game assets. Okay, here game assets. Okay, game assets management. So in Unity, it's easy because you have the library to manage all the assets, and then it's a GUI form. A good game engine, you need to manage the resources very well because there are hundreds or even thousands of the objects inside the video world. There are lots of character, there are lots of particle effect, and inside the scenes you have lots of the pops in your video world. So you have to think about this kind of resources management. They are going to manage the model, the texture, the plabs, the audio trips, the event, entry scenes, etc., etc., etc. Okay. So yeah, Unity, they have the resources bundle for you to manage the resources. But most likely I would say that Unity, the main problem of Unity is about the resource manager, or we call it garbage control, etc. So it always eat all of your memory. Okay. So they do not have a good management about the garbage control, and then they cannot release the memory, release the resources inside your games. So why Unreal they can have a better performance because they have a better resources management, and this one is the difference between the game engine. Sometimes we say that why Unreal is more expensive than the Unity 3Ds, or why Oracle or the DB2 is more expensive than the SQL Server or MySQL. The reason is not about the function. Their function that provide are almost the same. So the difference are about their non-function requirements. So they provide better management control. They provide better memory control. Okay, memory management for it. Okay, and then the rendering engine. So yeah, the difference between the Unreal and also the Unity is also about the rendering engine. They provide more realistic Unreal. They provide more realistic rendering. They contain lots of the light tracing. Okay, light tracing, which is a physics calculations. Okay. And then the light tracing is really important inside a video without lighting. For example, here, without lighting here, all the things inside the 3D world is just like a 2D. Okay, because all the for example sphere or the wall here, they contain the same color, right? Without lighting, so you cannot have the gradient. Okay, gradient shader. Okay, gradient shading here. Okay, and then it doesn't look like a 3D world. So this one is, yeah, this one is 2D, right? But here, when you look at this one, it's 3D. Okay, the only difference is the lighting. Okay, the more expensive 3D engine, they can provide more lighting effect, ray tracing effects for you. Okay. Unity now they are increasing their ability about the light tracing, but of course compared with Unreal is another world. Lighting, yeah, we'll go deep into this part to hear about what's going on with the lighting. So here, this one, length, okay, length, always remember his name. So we have the lighting here, and then when we're changing the lighting source, okay, lighting source, the aim mat, okay, aim mat. So you change the effect, you change the visual effect of length. So how it works? So just a reminder about your mathematics in secondary school. So every knob they have a X, Y, Z position, right? So when you have two pawns, okay, so it can become a vector. So you have the A vector, and then you have the B vector. Okay, with A and B vector, so you can use the cos product to generate a normal. Okay, here to generate a normal of your face. So here you have a triangle, you have a face, and then you can generate a normal which is perpendicular. Here is perpendicular to your face. So here is the calculation about the normal. So when you have the A cos B, so you have this kind of major settings, okay, and then you are going to calculate the x value by using this part, and then the y value by using this part, z value by using this part. Okay, so you have a calculations about a a2 times b3 plus a3 times b2, etc., etc. Okay, and then finally you can calculate the x, y, z positions. So for the details, you can go back to the computer graphics, or you can go back to your secondary school mathematics. But in our game development, most likely we only use the cost product and then pass all the things to our computer to handle this kind of matrix calculations. So finally, we have the normal, which is perpendicular to your face here. Yeah, perpendicular to your face. Why we need to calculate the perpendicular of your face? Because we want to calculate the angle between the normals, that means the face, and the light source. Okay, the light source and also the normals. So we want to calculate this angle. To calculate this angle, so we have another calculations called dot product. Okay, dot product. Cos product return you a vector, and dot product returns you a value. And this value is the angle between the light source and also between the normals. Okay, so if the angle is more, that means that the lighting is directly on your face, so it will becomes brighter. So if it's the angle is large, so it's away from the light source, so somehow it will become the dimmer. And yeah, this is the calculation of your cost product. So you calculate the magnitudes of L, magnitude of N, and then you use the cosine theta to calculate. Okay, so if we do it like that, so we can know the angle here. So by using this kind of calculations to calculate the angle face by face. Okay, for each face we have an angle. So even for the whole polygon, if you have the same color, because they have different angle according to light source, so they have different interactive, and then it looks like a 3D model. Okay, so it really depends on how you want to calculate. For example, this one. So if you have the GPU, you can done this kind of calculation. You can done cost product and dot product. But somehow, if you do not have the GPU, so this, as I mentioned before, the cosine theta is only calculated by the matching table. Okay, they cannot calculate the exact value. They can only calculate the range and then return by using a matching table and then return to you. And yeah, another library for the inside the game engine is animations. Okay, so as I mentioned before, the animation is using the skeleton 3D animation. We are using the skeleton. Okay, we have the X, Y, Z position to record all the positions of the joint. Okay, and then the joint control a part of the polygon. Okay. And then when we record the XYZ position of hologram film by film, so they will pay the animation. 3D is like that. 2D is only a series, okay? A series of picture. So they pay it together, and then you can find the 2D animations. So for 3D animations, so we pay the animation, but somehow you can move inside the 3D world, right? You can move inside the 3D world. So we need some 3D manipulations inside the 3D world. don't think that we have lots of the 3D manipulations. For example, you have jump, you have I don't know, dash or other things. By the way, we only have three. So it's called translate, rotate, and scale. Okay. For example, jump. That means where we only change the Y positions. Okay, we only change the Y positions. Okay, and then pay the animation of jump. So it's called jump. So we use the translate together with paying the animation together, and we perform the jump actions. So here is the matrix for you to handle the translate, rotate, and also the scale. Okay, so all the mathematics in secondary school. So we use the 4x4 matrix to set the new positions of translate, to set the rotation. This one is y-axis rotations. We use the cosine and the sine, and then we have the scale, the new value of the animations inside the scale. We put it inside and then do all sorts of things. So calculation is really complicated, right? But by the way, we have the game engine, we have the library for us to call and then do the calculation. So mostly the inside the directs or inside the other game engine is easy. We just call the API and then we can perform. For example, we want to move the car here. We moved on from the origin to somewhere else. Okay, so we just call it create translations and then put the new matrix to it. So that means the new positions, and then put it into a new matrix and then apply into the car. So we can move the car. Okay, so that's easy. Scale, similar, right? Scale. So we have a car here and then we want to scale it double the size of the car. So we just put it 2, 2, 2. Okay, new X, Y, Z scale and then apply to the matrix. And then matrix apply to the car. So it turns into the new scale. So here you can make use of a assignment. In fact, this one is a programming task many years ago, right? Programming task many years ago, we asked you to use the program to change, okay, to change the positions and also the orientations of the fans, okay, how to change it to under the car to next to the car, okay. So if you have time, you can use your paper and pen and then do this kind of, whether I should apply the rotation among the x-axis, y-axis, or z-axis, and then how we can move it, etc. Okay. And here is the answer. So we first apply the rotation among the x-axis, okay, and then we use the rotation among the y-axis, and then we change their positions, okay. So yeah, if you have time, you can try it using the program to control all the things instead of using the GUI because you are a programmer. And sometimes inside the Unity 3D, you are not allowed to use the, we are dynamic, right? We are not all the things are pre-record. So somehow we still need to use the program to do this kind of modification or this kind of manipulation. So you can try these examples. Visual effects. So yes, visual effects here. So beside the 3D model, or I will say that for the 3D model, so all the things are pre-record. So we cannot destroy the 3D model. Otherwise, we need to prepare another 3D model. So if you want to present a people is killed or is killed by weapons or is killed by bullet. So inside a game, so somehow we use the original model, but we add a particle effect. Okay, for example, blotting, for example, I don't know, exposure or other kinds of things, right? You put some visual effect onto it. Okay, so particle effect is one of the well-known or commonly used visual effects. So for all the magic, if you want the fire, smoke, water, etc., so you give the particle effect. Okay, so for the bullet holes and then the footprints, we will not destroy the original 3D model. For or on the 3D character, we will not destroy it. So we put some visual effect on the 3D model and then do this kind of thing. Visual effect is also used for the environment mapping and also light light mapping. For example, Mario, right? So if you Mario take a star, so it become a shiny 3D Mario. Okay, you become a shiny, and then for this shiny effect is controlled by the environment mapping. It's controlled by the shader. That means the visual effect. Okay. So visual effect is not a realistic thing in the video world, but somehow it's a common thing in the game world. Okay, it's a common thing in the game world to replace or to reduce the use of the memory, to reduce the use of the resources and model. It saves lots of the development and save lots of the calculations. Besides that, we also have different kinds of library inside the game engine. For example, you have the message system that you want to talk with the others. You have the dynamic game object model that you want to change the video object. You have the real-time agents based animation to change the animations of about your NPC non-player control unit. You also have something deal with your network. Okay, for example, deal with hardware and also network for I/O. Okay, for example, streaming or for the player versus player games or other kinds of resources management. So there are lots of the things inside the assets. So if you are interested, so perhaps later we can go deep into this kind of things, how the game object is defined, and then yeah, they go to different parts of things and match with the science, and then match with the reference, match with the texture, and then becomes the complete games. So here are some information, so you can search this kind of information. And
welcome back, Sethling here.
Yeah, have a
You're
look
watching
with
a
the
skilled
AI.
player play
So
Super
this one
Mario
is the
World.
Mario
But this
IO
player is not
for you to
human.
perform the
It's a computer program I wrote
AI
called
testing.
Mario.
And then you have
This
also
program
lots
started
of the
out knowing
physics
absolutely
that
nothing
you can
about
try.
Super Mario World or Super Nintendo's. In fact, it didn't even know that pressing right on the controller would make the player go towards the end of Welcome back, Sethbling here. You're watching a skilled player play Super Mario World, but this player is not human. It's a computer program I wrote called Mar.io. This program started out knowing absolutely nothing about Super Mario World or Super Nintendo's. In fact, it didn't even know that pressing right on the controller would make the player go towards the end of the level. It learned all of these things through a process called Neuroevolution. In this video, I want to teach you about how Mar.io learned to beat this level, Donut Plains 1, what his brain looks like, and how it's all based on actual biological evolution. So let's start out by actually looking at Mar.io's brain. Let's play it again, but this time we'll look at Mar.io's brain as it's making the decisions of what buttons to press. It's going to look a bit complicated at first, but don't worry, I'll help break it down for you. This structure of colored lines and blinking boxes is called a neural network. It's a simple mathematical model for how a brain works, but it can produce some very complicated behavior. With enough computational power, a neural network could come close to simulating a real human brain, but modern technology isn't there yet. On the left side you have the inputs. This is what Mar.io sees. It's a simplified view of the level. The white squares stand for blocks the player can stand on, and the black squares stand for moving objects like enemies or mushrooms. On the right side you have the outputs. These are the 8 buttons that Mar.io is able to press by using its neural network. In between the inputs and the outputs, all those lines and boxes, those are the neural network. Each free-floating box is called a neuron, and the lines connecting those boxes are like the axons and dendrites in a human brain. At any given time, only some of these neurons and connections are actually being used, and this is what people talk about when they say you only use 10% of your brain. The neural network you're seeing is a pretty complicated one, and it got so complicated as a result of a 24-hour evolutionary learning session. So, to explain how neural networks work, let's rewind about 24 hours and look at how the whole process started. This is what Mar.io looked like at the beginning of its training session, all the way back in generation number 0. The program is probably even dumber than you thought at this point. Often it just stands there and doesn't even press any buttons. If Mar.io stands still for too long, it'll cut off the simulation and try the next neural network, so it's mostly just jumping from one simulation to the next. But occasionally, the neural network says to press the right button, and the player starts walking right. The behavior isn't complicated, but it's enough to make at least some progress in the level. Let's take a look at a sample neural network to understand just how that works. This is one of the randomly generated neural networks that appeared in the first generation of the simulation. There are some green lines and a red line, and one neuron in the middle. Here's how it works. A green line is a positive connection, and a red line is a negative connection. A green line reading from a black or white square will turn its output the same color. A red line reading from a black or white square will turn its output the opposite color. In this case, the green lines read from the platform that the player is standing on and make the neural network press the right button as long as the player is standing on it. However, when the red line reads a black square representing one of those caped Koopas, it presses the A button and makes the player jump. This puts the player in a position where the green lines are no longer reading a white square, so the right button turns off and Mario just stands there. This is a really basic example that illustrates how a more complicated neural network might operate. The more lines and neurons you have, the more nuanced the decisions can be. So, how exactly do we get those more complicated neural networks? The answer is evolution. When Mar.io gets further right on the screen, its fitness goes up. In this case, fitness is a function of how far right it gets and how quickly it gets there. Only the neural networks that produce the highest fitness are selected to be bred, creating the next generation. It took 34 generations of genetic breeding and fitness evaluation before Mar.io was able to finish the level without dying, and get a fitness score above 4,000. You can see there were several places it got stuck for a few generations, but it always evolved out of those ruts. Let's take a look at a few of those ruts. You can look at the top left corner of the screen to see what generation number each rut occurred on. This process of picking the fittest individuals from each generation, breeding them together, and adding random mutations very closely matches the actual process of biological evolution that took single-celled organisms and produced intelligent humans. That's the power of neuroevolution. And though we don't yet have enough computational resources to produce something on the level of a human brain this way, it's kind of neat to see what it can do on one of my favorite games. I didn't come up with this idea on my own. This algorithm is called NEAT, which stands for Neuroevolution of Augmenting Topologies, and it's based on a paper by Kenneth Stanley and Risto Mikulainen. It's a really great paper that describes how to use genetic algorithms to build up neural networks from bare bones, without presupposing the best structure for the neurons and their connections. It also includes some really cool ideas for separating genomes into species, which a lot of genetic algorithms don't really try and do. I wrote Mario from scratch in Lua as a plugin for an emulator called BizHawk. As I close out the video, let's take a look at the fittest neural network in each generation. It's kind of cool how sometimes you can see them make modifications to each other and improve performance, but sometimes an entirely new species becomes prominent and dominates the others. If you'd like to do more reading about the concepts I talked about in this video, I provided some links in the video description. I had a lot of fun working on this project and I learned a ton. Hopefully you learned something too. That's about it. Thanks for watching.